Hello, I'm Lisa Shepard, and I'm a postdoc working with Angela Speck at UTSA. My research focuses on the dust which forms around oxygen-rich AGB stars. To do this, we created a program which we call MiraFitter. This allowed us to use a simplistic method to investigate spectral features in a sample of optically thin Mira variables. Now, radiative transfer modeling has often been used to analyze spectra and obtain a match to the overall spectral energy distribution with certain parameters. So why not just use radiative transfer modeling? While RT modeling should allow us to build a spectrum that includes all contributions to the observed spectra, we are hampered by a lack of detailed or appropriate laboratory data for such modeling. RT modeling cannot include many different potential astrominerals because there is a lack of complex refractive indices available. This limits the application of RT modeling if we want to determine the detailed mineralogy of the dust. In some cases, usually very optically thin scenarios, we can simply eliminate a continuous contribution to the observed spectrum to isolate any observed features and measure their basic spectral parameters. To begin modeling a stellar spectrum, we know that as long as the dust shell isn't too opaque, the total flux observed is due to the flux from the star and due to the dust surrounding the star. Subtracting the stellar flux gives an equation for the dust, which is often simplified. Here, C is a scale factor that depends on the number of dust particles, their geometric cross-section, and the distance to the star. Q is a composite value including contributions from all dust grains of various sizes, shapes, crystallinities, and compositions. B is the Planck function for a black body of temperature T. In the literature, this equation has been applied to the entire spectrum, including the star, or it has been applied after the subtraction of a stellar or black body spectrum. I first determined the sensitivity of the position of spectral features to the simplification of the equation. This project started with an analysis of several methods of continuum elimination using the archetypal dusty star Mira to account for the continuum emission in the observed spectra. Plotted here is the spectrum of Mira obtained from the Infrared Space Observatory shortwave spectrometer, shown along with the blackbody curve for 3420 Kelvin. The ISO data was taken when Mira was at a maximum, and from the spectral class at that date, we know the temperature. Also plotted here are IRAS flux measurements at 12, 25, 60, and 100 microns, and BVJHK filter fluxes. However, they are not all taken at the same date as the ISO data, so they are shown here just as constraints on the graph. There is a V-band flux measurement for the same date as the ISO data, and that was used to normalize the plot. The red line represents our star, and everything above that line is the dust excess. Although a black body may not be representative of the star exactly, we are not sensitive to the precise temperature. Looking at our equation for flux, keep in mind that the Q value times the Planck function covers all the wavelengths. While silicate dust gives off most of its emission at the two peaks, there is still emission in all wavelengths, and it is temperature dependent. Here are the different continuum elimination pathways which we investigated, and all of these start with the total flux coming from Mira and the surrounding circumstellar dust. With the total flux, we either divided by a stellar blackbody or divided by a modified blackbody with an emissivity index. Then we subtracted the stellar blackbody to leave a dust-only flux. That dust-only flux was divided by a modified blackbody with an emissivity index, and we did that for a few different temperatures, which you can see here. Another method was to take the dust-only flux and subtract the dust continuum, and then divide that by a second dust blackbody continuum at 600 Kelvin, and that removes any temperature dependence. For more details, please see our publication, which is referenced below. When I talk about the modified blackbody with a certain emissivity index, what I mean is that it has the same effect as summing many blackbodies of different temperatures. Looking at the total flux of the star and the dust surrounding it, here are the two examples after continuum elimination. On the left, you can see the total ISO spectrum divided by the modified blackbody, and on the right is the total spectrum divided by a stellar blackbody at 3420 kelvins. Here we can see the stellar blackbody subtracted spectrum. In other words, the total dust spectrum of Mira, plotted together with the dust continuum blackbodies. The different temperatures which we chose to use were 1000, 1500, and 2050 Kelvin. Approximately 1000 Kelvin is the typical silicate glass transition temperature. Above the glass transition, the silicate grains will either form directly as crystalline material or an amorphous solid will begin crystallizing. The other temperatures we chose coincide with the condensation temperatures for olivine and pyroxene at about 1500 kelvins. And 2050 kelvins was used because it provides the best fit to the total dust spectrum without any theoretical considerations about dust stability. Here we can see the effect of using different dust continuum elimination. This is examining the dust-only flux. Each column shows the temperature labeled at the top for the black body used for continuum removal. The top row uses a modified black body and is the total dust spectrum divided by the black body dust continuum for that column. The middle row shows the total dust spectrum with the dust continuum black body subtracted. And the bottom row is the same as the middle row, but with a 600 Kelvin black body divided out. For our measurement results, we looked at the peak position near 10 and 18 microns, the very center position for these as well, and the full width half maximum of the 10 micron feature. For the 10 micron feature, the peak position is consistent for all pathways to continuum elimination that start with the subtraction of the stellar black body. The 18 micron feature is more sensitive to the next step in the continuum elimination. For the pathways that do not start with subtracting the star, even the 10 micron feature position varies. The barycentric positions for both the 10 and 18 micron features show similar trends with the 18 micron peak position, showing that division by a continuum has a major effect on how we measure the position of the spectral features. I would like to point out that if we take the dust-only spectrum and then divide by a modified black body, that has the same effect as subtracting a dust continuum and then dividing by second layer. The barycenter has similar results. While they are not equal, they are quite close. Then the next step is to compare two spectral parameters of sample glasses. And if we compare the measurements with those here, we see that it is similar to cosmic silicate. The graph on the right shows calculated Q values or absorption efficiency factors for samples. These Q value spectra are stacked to demonstrate the shift in wavelength of the peak near 10 microns with composition. To summarize, the precise pathway to continuum elimination can have a large impact on the peak position, barycenter, and full width half maximum of the spectral features, which tells us that this is important because it may lead to misidentification of dust species in space if you are not using the correct pathway. I also found that I could change the temperature or the emissivity index quite a bit before it has any effect on the positions of the spectral features. So we do not have to be exactly right on those numbers to get the same measurements. Although the black body may not be representative of the star exactly, it's not super sensitive to the precise temperature, so it works. And finally, taking the dust-only flux and dividing by a modified black body gives the same result as fitting multiple dust shells to the spectrum. Thank you for watching my presentation, and if you would like to contact me, my email is listed here below.